Now if we look at this diagram, this is what single cycle execution would look like. Now let's say this is our instruction 1, and if this is the clock cycle or clock period of one instruction, once this first clock cycle is over, let's say this is clock cycle, this is our first clock cycle, let's say 1C, this is 2C, and then this is 3C, and so on. Then the next instruction would start here, and then the next instruction would start here, and so on. So this is how the instruction would execute in a single cycle pipeline. So this one is instruction 1, and then we have instruction 2, and then we have instruction 3, and so on. What this means is that once instruction 1 is over, only then instruction 2 can execute, and once instruction 2 is over, then only instruction 3 can execute. But if we look carefully, then when instruction 1 is executing, let's assume that it has three phases. One is fetch, one is decode, and other one is executing. Similar situation is here and here, as these are life cycle with that goes with every instruction. So fetch, decode, and execution. So when instruction 1 is executing and it performs the fetch operation, then whatever the hardware that are involved in the fetch stage has nothing to do until next instruction comes in. So during the decode phase and in the execution phase, the fetch hardware is idle. But we cannot keep hardware idle if we are to achieve high performance from the system. To overcome this solution, we come up with a solution which is called pipelining. In pipelining, what we can do is we would break the instruction execution into more phases. Let's do it like this. It's fetch, decode, execute, memory operation, and then we call it write back. So let's say this is instruction 1. So instruction 1 is performing fetch, and all these fetch, decode, execute, memory operation, and write back would take one clock cycle. All of them would take let's say this is C1, this is C2, this is C3, C4, C5, next it will be C6, C7, and so on. So this is how it goes. Now when after clock cycle C1, instruction 1 finishes its fetch stage and enters the decode stage. That means whatever the hardware involved in the fetch stage are free. So what we can do, we can start executing another instruction here, and so fetch, decode, execute, memory, and then write back. As you can see that at clock cycle 2, what we are doing, we have two instructions in the system. One instruction, that is instruction 1, is performing decode in clock cycle 2, and instruction 2 is performing fetch. So they're working on different hardware, different portions in the data path. Now at clock cycle 3, what we can do is we can have this kind of scenario. Fetch, decode, execute, memory, and write back. Let's say this is clock cycle 3. In clock cycle 3, instruction 1 is performing execution. Instruction 2 performing decode. So fetch is again free. So instruction 3 can start executing fetch. Next, if we extend it further, then we can see that this fetch, decode, execute, memory, and write back. And this is I4. Again, at clock cycle 4, that means here instruction 1 performing memory operation, instruction 2 performing execution, instruction 3 performing decode. So fetch is again free. So instruction 4, we can feed instruction 4 into the system, and that can work in the fetch hardware, and this process would continue. Now what if we consider this method with the a single cycle implementation, what we have seen is that in executing 3 instruction, we have executed 3 instruction in a single cycle, and that would take around this much time. And but if we look carefully, then around this much time we have executed more than 3 instructions in our pipelining design. This is called pipeline design. So if we keep drawing this design, then we would see that in a single cycle we can, if we have I5, then we would see that instruction in clock cycle 5, instruction 1 will be over, instruction 2 will perform a write back operation, a memory operation, and so on, which means after clock cycle 5, on clock cycle 6 onward, each clock cycle will complete 1 instruction at a time. But these clock cycles are much smaller. These clock cycles are much smaller than this clock cycle. So pipeline would give us much better performance than compared to a single cycle implementation, because pipelining makes better utilization of the hardware. As a result, gives more throughput from the system, or generates more throughputs from the system. So MIPS pipeline, in pipeline we already have seen, we have instruction fetch, instruction decode, execution stage, memory stage, and write back stage. These are the 5 stages that we have. We already have seen it in the previous slide. Now pipeline performance. Assume time for stages is 100 picosecond for register read and write. So let's assume that 100 picosecond is required for register read and write. That means when we are reading the register, that is performing the read operation, and when we are performing the write back operation, it takes the similar amount of time, and 200 picoseconds for other operations. Now let's consider load. Instruction fetch 200 picosecond, because it is memory read operation, and then register read, it is 100 picosecond, ALU operation 200 picosecond, memory access 200 picosecond, register write, that is write back operation. Total it requires 800 picosecond. For store, 200, 100, 200, 200. Store has no write back, so we do not need any time here. So this is 700 picosecond. R format 200, 100, 200, and it does not have R format instruction. The instructions do not have any memory operation, so we do not need this. So it will be 600, and BEQ to 200, 100, 200, and it has none of this, so it requires as 500 picosecond. We can see that here that load takes the longest amount of time. We already have discussed it in the previous slides. Now performance issue, if we see the diagram here that we have seen a couple of slides back, see we are performing load instruction or executing load instruction, fetch, register operation, ALU, data access, and register operation. So this would take 800 picosecond, then 800 picosecond, and then 800 picosecond. So 3 loads would take around 2400 picoseconds. Now, using pipelining, see how much time you would need. This is load 1, so this is instruction fetch in second clock cycle. First instruction finishes its fetch operation, so second instruction can start executing. Similarly, after second instruction goes to the decode fetch, third instruction can come in. Now, if we consider this is the time that it would require to perform this or complete these three instructions, this is around 1300 picosecond. So we can see the difference. This is 2400 picosecond and this is 1300 picoseconds. And if we continue feeding more instructions inside the pipeline, we can see that the time required to execute each instruction is reducing much further. So the speed up, if all stages are balanced, that means if all stages takes a similar amount of time and there is no issues associated with the stages, then time between instructions, that is in case of pipeline, would be time between instructions. In case of non-pipeline, that is, let's say, a single cycle data path over number of stages. If not balanced, speed up is less. That is different issue. Speed up due to increased throughput. Okay. So pipeline and instruction set design, this can also be a call as why pipeline is easy. One point is all instructions are 32-bit. In case of our MIPS instruction, all the instructions are of 32-bit. We do not have any variations here. So it is much easier to design a system if you know that no matter what happens, all the instructions are going to be 32-bit. Few and regular instruction formats. We have only three formats: R, I, and J. These are the three formats that we have. Load and store addressing. We only have two memory operation. One is load and the other one is store, and that is also in the third stage and the fourth stage. And memory alignment, memory access takes only one cycle. Okay, so these are the points which makes pipelining easy to implement. Hazard. This can also be called why pipelining is difficult. One is structural hazard. One issue with pipeline is that if multiple instruction tries to utilize or access the same hardware component at the same time, this would cause structural hazard. Data hazard, when one instruction depends on the output of another instruction, but that is still not ready, so this would give data hazard. And control, similarly, with after before in before crossing certain stages, we are not sure whether to take a branch or not, or jump branch. Basically jump is not it's unconditional. So in case before crossing few stages, we do not know whether to branch or not, but by that time there might be few instructions which already have entered into the pipeline. So what to do with those instructions if we are to take branches? So this is called control hazards. Structural hazard. So what is structural hazard? Structural hazard is conflict for use of a resource. Conflict for use of a resource. Now what this means is that let's say two instructions are trying to access the same physical component. Let's say physical memory. One could be instruction memory and other could be data memory. We know that both of them are on same RAM. It's just physically separated. One is reserved for instruction memory, and the other part is reserved for data memory. Instruction memory and data memory. Now, if we execute load store operation, and at the same time in the same cycle, there might be an instruction fetch, which means load store, which is operating on data memory, and instruction fetch, which is going to operate on instruction memory. Now, to load store to execute, instruction fetch would have to stall for that cycle, which means there cannot be any instruction memory access on that cycle. There will be only data memory access, that is load or store operation or instruction, could execute. This would create a bubble inside the pipeline, which we call stall, which means one clock cycle of wait. Hence, pipeline data path requires separate instruction and data memory. So how can we avoid this scenario? How can we avoid this scenario? This can be easily avoided by having a separate data memory for a separate memory for instruction, physically separate memory for instruction, and physically separate memory for data. This can be managed by instruction cache and data cache. Data hazard. What is data hazard? If we look at this example, then we would see that this add instruction, this this add instruction is a S naught, T naught, and T1, which means whatever the result that we can get after performing addition with the of the content that is in T naught and that is in T1 will go to S naught. This is not the issue. The issue is this S naught is source 1 in the second instruction. Now, when can this S naught get updated? This S naught get updated during the write back stage. Once the write back is performed, only then S naught gets updated. But when do sub needs the value of S naught? It would need the value of S naught during the decode phase, because we know that during the decode phase the system identifies the source and destination registers and performs a read operation on the source register. So we need S naught to be ready. We need S naught to be ready when the decode operation is in process. But according to this sequence, it is not possible. S naught will only be ready when the write back operations are done. How can we execute these two instructions then? Because until S naught is ready, if we execute sub, then the value that S naught will have is not the value that we are looking for. That is, we need the updated value of S naught, that is here. So what we can do, we can introduce two stall or two bubbles. Let's see. This is our add instruction. That means the first instruction. So it fetches, then decode, then execute, then memory operation. But this has no memory operation, so it would just wait there, and in the next cycle it would perform the write back operation. We introduce two bubbles, so one after this two bubble on the third cycle we start instruction fetch for sub, then decode, which means we are performing a read operation on the register file. C, write operation is already done in the half clock cycle, first half of the clock cycle. So read operation can be performed the second half of the clock cycle. So just by introducing these two bubble, we could perform the execution of these two instructions. But there is a big question, and that is, we always try to achieve the maximum performance and really high throughput from the system. But if we keep on introducing these bubbles into the system, that means this is not increasing the throughput. Instead, it is decreasing the throughput. So we need to come up with design that would get rid of these bubbles. One solution for that is forwarding. Now, if we have the same instruction here, the add and the sub, and if we see if this solution is possible or feasible, then let's start with add instruction. This is fetch, this decode, this execution, and we do not have memory operation in add instruction, and then the write back. Now the question is, when ALU exits the result, that means the addition of T0 and T1, this result doesn't change. That means this link, whatever the result this link carries, is the final result. So, and we know that the following instruction after the add needs this result. So, what we can do, we can forward this value to this immediate link. If we forward this, then see the scenario that we perform fetch, decode, execute, memory, and write back of the first instruction, and in the second clock cycle we start sub instruction, perform the fetch, and we perform the decode operation. Now when we are performing the decode operation, we still do not have the updated value of s naught, but after this clock cycle, we have the updated value of S naught. So we can replace the previous value that is read from here through providing updated value of S naught through this link. So in the execution stage, that is the ALU gets the updated value of S naught and can perform the remaining of the operation, that is the sub operation. So load use data hazard. In the previous slide, we have seen that we reduce the we get rid of this bubble just by using the forwarding method. But for load, let's see the this load instruction. So this load instruction, it fetches, decodes, execute, memory operation, and write back. Compared to the add instruction, where we had no memory operation, but for load we have memory operation. So uh, it's a memory operation and it's memory read operation, and then write back, it's register write operation. Now consider this sub instruction. In this sub instruction, destination is T1, T2, source 1 is S 0, and source 2 is T3. This S 0 is source 1 here, which means we need to update this S 0 before a sub can access S 0. To do that, this write back needs to be performed. But if we look carefully, then this write back holds the value that is read from this part of the memory, that is being read from this part of the memory, which means this link carries the data that is going to be that is written back to this register, that is register S naught. Now look carefully. In the when we had add and sub, we we just get rid of the bubble. There weren't in bubble, because in case of add, the final result was the result that ALU was giving. So the output of the ALU was the final result. But in case of load, if you look carefully, then the output of the ALU is not the final result, is the address where the read operation should be performed. So if we forward from here to here, then we are not forwarding the data, we are forwarding the address. To make this work, what we need at least one, we need a bubble here. And if we give a bubble, that is a stall, and start our sub instruction one clock cycle later, then what would happen? This is fetch, this is decode, and we are reading the register, and from this memory link we are forwarding the value of S naught to this link. By doing this, whatever the value we have read here, we perform the read operation here, it's getting changed by this forwarded value, and then the rest of the stages can be performed. This slide shows the number of cycles that we may need and how we can reduce the cycle by rearranging the instructions. So if we see here the first load, it would take 5 clock cycle, because load has load or any instruction needs to go through fetch, decode, execute, memory operation, and write back. So each stage would take 1 clock cycle. So in total 5 clock cycles. So to execute the first load, we need 5 clock cycles. And then after each clock cycle, one instruction will be executed. So for the second load, we need another one. See, this T2 and this T2, they are similar. That means this T2 is dependent on the T2 of second load. So we need to wait till the write back is performed, or at least the memory read operation is performed. If we have the forwarding mechanism enabled, then we will need to have only one stall here, and the add would take one clock cycle, store one clock cycle, load one clock cycle. Then again we have forwarding here, so this will be one clock cycle, and then add one clock cycle and load one clock cycle. Let's see how many cycles do we need. 5, 6, 7, 8, 9, 10, 11, 12, and 13. See, there are 13 clock cycles are there. Now, is there any way we can reduce the number of cycles? What you can do, since this load is independent, it is not dependent on any other instruction. What we can do, see, we have one stall here. We have one stall here. So we can feed this load into this position as it is. You can see here. This is the third load. So if we do that, then this one would take 5 clock cycle. This one would 1 and 1, and then this one, this will be 1, this is 1, this is 1, and this is 1. So how many clock cycle do we need? 5, 6, 7, 8, 9, 10, 11. See, we need 11 clock cycle for when we rearrange the instruction. That means we could save 2 clock cycles. Control hazard. Branch determines flow control. So if we have instruction 1 and then instruction 2, instruction 3, and so on, then after instruction 1, in regular scenario, PC plus 4 will be instruction 2, and then PC plus 4 will be instruction 3, and so on. But if we have branch in between this, then we do not know for sure which instruction would be executed. Let's say in between instruction 2 and instruction 3 we have a branch instruction. So we do not know whether instruction 3 will be executed or some other instruction needs to be executed, or needs to be fed into the pipeline. So fetching next instruction depends on the branch outcome. This only can be we can only tell whether to branch or not after we are done with the execution stage. That is, ALU perform the subtraction operation. Pipeline can't always fetch correct instruction. Still working on the instruction decode for branch, which means still requiring the branch decision to be made whether to branch or not. In MIPS pipeline, need to compare registers and compute targets early in the pipeline. Add hardware to do it in the decode stage. This is one option. If we can add hardware in the instruction decode stage, it could perform the test and would tell that this is a branch instruction and the branch will be taken. So the next instruction will be from branch target address, not from PC plus 4. So not from PC plus 4. But for that we need to add extra hardware there. Now stall on branch. Wait until branch outcome determined before fetching next instruction. This is one option which is a defensive option, where let's say this is our instruction, this is the first instruction and this is the second instruction. So second instruction is branch, so it performs the ALU operation, and after the ALU operation the decision is made whether to branch or not. But the next instruction after the branch is still waiting, the pipeline is still waiting to select the next instruction. This can only be done after the ALU stage. So what the pipeline would do, pipeline would introduce bubble or stall. So pipeline would introduce a wait until the decision comes in. Once the decision is in the hand, the next instruction enters the pipeline. But by that time, we have lost quite a bit of time. Branch prediction, longer pipelines can't really determine branch outcome early. Longer pipelines means if there are loads of instructions coming into the pipeline, so it is really hard to determine the branch outcome early. Stall penalty becomes unacceptable in those cases. Predict outcome of branch, only stall if prediction is wrong. one prediction, one option can this can be one option. In MIPS pipeline can predict branch not taken. So this is one option that can be taken, that can be considered, that branch will not be taken. So no matter what the instruction is, it will always be sequential execution. So if we consider this and take the next instruction, that is after the branch instruction, and feed it into the pipeline, this is one option. And research has shown that around 50% cases that prediction is correct. That means around 50% cases the branch will not have to be taken. Fetch instruction after branch, no delay. So in this case there will be no delay, at least for 50% cases. So this is one example when where it is thought that the branch will not be taken. That is that 50% case example. So see, there is a branch instruction. So the system did not wait for the outcome to come. That means whether to take the branch or not. It just taken the next instruction. So this is a prediction is correct in this case, so there is no penalty. But in this case, the prediction is not correct. So what happens is that after the ALU stage, when the subtraction is done and it is found out that there will be a branch, so we need to introduce stall. That means wait, and then once the branch address calculation is done, then the next instruction enters the system. But in this case, we lose quite some time. So more realistic branch prediction, static branch prediction based on typical branch behavior. Then example could be loop and if statement branches, or dynamic branch prediction. Hardware measures actual branch behavior, that is record recent history of branch. Assume future behavior will continue the trend. So based on the previous analysis, assume that the future behavior would be like what it was previously. So it could be one option. Now, what is the pipeline summary that we can say now? Pipeline improves performance by increasing instruction throughput. We all know that in case of single cycle data path, once one instruction is done, then the next instruction comes in. But in pipeline, once one instruction completes the fetch stage, then next instruction can start the fetch operation. So executes multiple instructions in parallel. Each instruction has the same latency subject to hazard. This is the tricky part, because pipeline introduce the structural hazard, data hazard, and control hazard. Instruction set design affects complexity of the pipeline implementation. This is depends on the instruction set architecture and how they are designed.